writing machine-independent programs. We know that if we use cross-platform compilers and libraries, then we can recompile the same program to similar architectures, like conventional CPUs, for instance. But if we broaden or increase our expectations, then this is not the case anymore. We cannot take the same program and recompile it to different architectures, like conventional CPUs, FPGAs, or distributed systems. So I'll take an example. Imagine you want to write a web application. No, let's say we want to write a distributed application like this. So we have two servers, one that provides this functionality, Q to R, so maybe it's a database and you can do a query and get a response. And you have another similar database server. And then on a third server, you have some service that takes such functionality and gives you a processed piece of data. And now you want a P. So how would we write this program? Well, we turn to our favorite language or library with message passing, and we start hacking. We're functional programmers, so we extract this server functionality, and we can at least implement server 1 and server 2 using this higher order function. And this server function, it takes a function f to serve, and then it receives messages containing a process ID to return to, an argument, then it applies the function and sends the result back to that process ID. And then it repeats that. So that's server 1 and server 2. Now, how do we write server 3? Well, it's probably an instance of the same thing, but it's not as obvious. So we scratch our chin a bit and twirl our mustaches. And okay, so we come up with something. We start by not using this server function. Okay, so we receive the from PID, which will be the client, and a to PID, which is the process ID of the server that we want to use. And then, okay, we send our own process ID to the to PID, which was the server we wanted to use, and we send something, and then we receive our result and send the result back to the from PID, which was the client. So as you can see, it got a bit complicated pretty quickly. And imagine if you wanted to do an even higher order function, or if you wanted to change one of these servers to actually have the function be located on server 3 or something. Okay, and then we can write the client by sending some messages. Wouldn't it be nicer if we could write these programs like this? So we write them as ordinary functions that we know and love, and just say where that function is located. And then we apply them like normal functions. And this is what I want to do today, and I want to show you how that can be implemented. It's not an entirely new idea. There are some other projects that do similar or the same thing. I guess one of the closest one is Lynx, and I think there are some people associated with that project here today. Anyway, we want to do this. We want to show the underlying execution mechanism and support higher order functions across node boundaries, but without sending code. And we want to do it formally and show that it's correct, and we also want pretty good performance. So we've tried we've tried some other approaches before. So we thought, okay, so we have some semantics models of programs that implement them as some kind of message passing networks. So why don't we do that? So this program is compiled to these very small components, and they're all communicating with message passing. But that's obviously too fine-grained, so we come up with a way to combine any two components into one while preserving the semantics, and we can control the granularity then with these annotations. So that works. We've tried doing this in 2 different ways, but unfortunately it's slow. But it doesn't require garbage collection, at least not for limited languages, which is nice. So I guess the takeaway from trying these exotic denotational semantic compilation methods is that they may be useful, like, for instance, if you want to compile to FPGAs, but in this setting, we better use more conventional methods. We can't just expect to outperform half a century's research. Okay, so we now turn to the idea of today, which is take a conventional abstract machine, put it in the cloud, extend it a bit so that it does communication, and all rejoice. So today, Krivine machine, we've also done the CCD machine before, and we're doing this in Agda, which means I can sleep at night. Okay, so our source language is PCF. So we have lambda calculus, natural number literals, operations on natural numbers, conditionals, and we have this at node term, and here the type node is the type of node identifiers. We're using the brain indices, so an example of a term here uses natural numbers for the variables like this. Okay, so the original Krivine machine looks like this. It's really nice, only 3 rules, extremely elegant. It's my favorite abstract machine. So yeah, it's only for the pure lambda calculus, but so if you have an application, then you construct a closure of the current environment and push it on the argument stack. If you reach an abstraction, you take a closure from the argument stack, put it in the environment, and we're using the brain indices, so the indices in the environment correspond to the variables. And if we want to run variable n, then we look it up in the environment. Simple. In Agda, it looks a bit more complicated because we have to be more formal, injecting to the right data types and stuff. But it's essentially the same thing here. And then to do full PCF, all of the other features like conditionals and operations, we have to add some more stuff. And in the argument stack, we also have some other kinds of continuations. But it's all fairly standard stuff. Okay? So now a Krivine net will be an instantiation of a network model with a version of this Krivine machine that we've extended to do message passing. So now what is a network model first? Well, we have 2 of them. So we can do synchronous message passing, and here either a machine in the network can take a silent step, and then it can do so at any time. Or if 2 machines at the same time can send and receive the same message, then they're allowed to do that. Asynchronous messages are done with what's usually called a message soup. So if one machine sends a message, we put it in the message soup, which is up right here. And then at some point later, a machine can receive that message if it is in the message soup. Okay, so a bit more formally, a synchronous network is a node indexed family of machines, and node was this type of node identifiers. And an asynchronous network is the same plus a message soup, which is a list of messages. And then when we extend the Krivine machine, we let the machine step relation have tagged messages on it, which can be send or receive or silent, or tau, some people can call it. Okay, and then we also extend the relation so that it sort of knows what node is currently taking a step. So this is node I taking a step. Okay, and then synchronous networks, complicated, asynchronous, more complicated. Okay, so now how do we extend the Krivine machine? Well, the basic idea is something we call remote stack extension. So first of all, we assume that the term T inside this node annotation T at B is closed. If it's not, we lambda lift it. Doing this means that we can assume that the environment is empty, which simplifies things a lot because we only have to care about the stack then. Okay, so to run a term T at B where we want to apply that to some argument, well, at the point where T at B is run, this argument will be on the stack of node A, which we start from. And then what we do is node A sends a pointer to its own stack along with its name and 0 to B. And B receives that, and it starts with an empty environment because, as I said, T was closed. And what this thing means is that I know that I have some arguments on a remote stack on node A, pointed to by pointer and with offset 0. And now if B wants to pop an argument, it doesn't need to send any messages requesting that or anything. It just increases this index, puts index 0 in the environment, so this thing in the environment refers to arg, this thing now refers to the rest, the continuation that's possibly on the stack on it. Okay, so that's the basic idea, and then when B has produced a value later, then it looks at its remote stack extension and can return to A. All right, and a key thing here is that now an environment element is not just local closures, it can also be a remote pointer, which contains this pointer and the node. Okay, and in the paper we show these properties. So we define a relation Rs and show that this is a simulation relation between the original Krivine machine relation and this distributed Krivine machine in a synchronous network plus, so the transitive closure of that. And using this result, then these two follow. So if we have related configurations and networks, then if the configuration terminates, then the network terminates. And same for divergence. And this way of showing the semantics with an abstract machine perhaps surprisingly also gives us a way to compile the terms. And a simple-minded way to do that is to implement the instructions or the rules of the abstract machine as macros in your target language. So for instance, you might compile this term in the original Krivine machine like this. So the whole term starts at empty, and then it starts by pushing the argument that corresponds to this blue part of the term, which is this code pointer arg, and then it reaches the lambda, pops the argument, then variable 0, and so on. All right. So we've done pretty much this, but with the distributed machine, and made a compiler targeting C and NPI. And now we're comparing the performance of this to an implementation of the original Krivine machine and to our old attempts at solving this problem. So the original machine is the baseline, and we see that our old attempts don't do very well in our benchmark. We don't have very many benchmarks because the intersection of the language features for these three toy languages is pretty small. We can't really do that much, but yeah. Anyway, so this is running on a single machine, just showing sort of overhead compared to a conventional compiler. We see that the distributed machine is doing pretty well. And then for distribution overheads, we rewrite these programs in the stupidest way we can think of to make them do a lot of communication. And then we see the difference to the same compiler, the difference in speed of programs compiled to the same compiler. So here again we see that the overhead for the most part is pretty high for the old GUI and GAMC compilers. Apart from this outlier, but since it's compared to itself and it did pretty badly in this previous benchmark, it still doesn't mean that it's very fast. Okay, so the distribution overhead is quite low as well for the distributed Krivine machine. That's the takeaway. Okay, so what we've seen is the underlying execution mechanism for Krivine nets, or for languages with seamless distribution, as we call it, and a bit of the formalization and the compiler, and we've seen that it has perhaps promising performance. And there are more details in the paper, of course. In the future, we want to work on the runtime system and how to tie that into the language and how to do fault tolerance and failure detection and stuff like that. And perhaps we will need garbage collection as well, depending on the language features that we put in there. Okay, so you can get all of this, the formalization, the implementation on Bitbucket or some other places if you want. Thank you for listening.
Questions?
Josef Henningsson, Chalmers. So, do I understand it correctly that data is sort of sent on an as-need basis over the network? So, I was wondering if you've been thinking about having more complex data like arrays, where it might be important for the programmer to have something to say about where they're placed, because it costs a lot of, it just costs a lot to send them over the network.
Yes. So this work doesn't deal with this, but our most recent work does. And there basically what you have is a notion of mobile and immobile code or data. And then, for instance, every library function would be mobile probably, because we want it to be possible to run it everywhere. But your database might be immobile, and you can do pretty much the same with data as well. So
okay, I'm looking forward to seeing more of that. Thank you.
Any other questions? Okay, let's thank Olle again.